Hello, everyone. I'm Tim Doiron, Senior Director of Solutions Marketing at Infinera. It's great to be with you. The title of our presentation today is Optical Innovations for a Greener Planet, Evolving Today's Networks while also reimagining tomorrow's. So we all know about capacity demand growth in our networks. We see it in our homes, we see it in our work, we see it in our entertainment, in our family behaviors. I thought I would cite a couple of different sources here. The first of which is telegeography, which anticipates a 10x capacity demand over the next 10 years in transatlantic subsea cable networks. That roughly translates into 26% growth on an annual basis. I also thought I would cite a recent ACG research study that Infinera sponsored, where we asked them to talk to a number of service providers about their anticipated capacity demand growth in various segments of their networks for the next 5 years. Interesting to note is that capacity demand roughly runs from 46% to 39% from the edge of the network, or the metro portion, all the way back through the core and the subsea network. So an obvious question for all of us is, what is it going to take for us to continue to support these types of capacity demands going forward, while also not just continuing to do it the exact same way? And what it's going to take, and what we all need, is, of course, technology innovations. We need innovations that let us transmit more information over longer distances with less equipment for the networks we already have. But we also need innovations that help us leapfrog forward, or really make step functions forward in terms of different architectures or a different way of doing things, so that we can really progress in terms of the amount of equipment and the amount of power and our overall carbon footprint that we're having to use to transmit and connect all of these networks and applications and handsets and smartphones and the rest. What are the tools in the toolbox that are going to help us realize these technological innovations and move us forward with regard to our environmental impact, while also meeting our increasing capacity demands? In the rest of this presentation, I break it down into 3 key areas: embedded optical engines and the evolution to 800 gig 5th generation technology. That's going to help us evolve our current networks and get more out of the fiber assets we already have in the ground. In the second part, we're also going to talk about pluggable optical engines, and specifically we're going to talk more about a technology we call XR optics that enables point to multi-point optical communication really for the very first time. That will help us change our network architecture and will help us reduce the amount of equipment we actually have in the network, and increase our flexibility to enhance those services and add capacity over time. Finally, the other area we'll talk briefly about is the evolution of compact modular optical platforms. These are important because we're really creating not only a pay as you grow model, but we're also creating a power as you grow model as well. So before we dive into either pluggable or embedded optical engines, how are optical engines created and what makes them up? And today's technology of advanced coherent DWDM engines contain both an analog front end and a digital signal processing back end. Infinera is a company that really, since its inception, has thought about deep vertical integration and the need for these pieces to not be separated and isolated, but to be co-developed, co-packaged, and really thought through in the development life cycle. Instead of using discrete components on the analog front end, as an example, Infinera actually develops its analog optical front end as a photonic integrated circuit on a wafer like you might think about for typical microprocessor or electronics type components. This has a great benefit in many different areas. Obviously, performance is certainly one of them. So is size and packaging. But as shown on the slide, it also gives us increased reliability and a reduction in the mean time between failure as well, because we're dealing with something that's highly integrated and waferized, if you will. So we already mentioned we have an analog front end and a digital signal processing back end. That certainly gives us the ability to take advantage of Moore's law, where we can populate more transistors in less space with less power over successive generations of technology and of process node evolution. And you see that reflected here in the graph over time, where the geometries and the size and the density is going up and the size and the geometry is going down, to a point where today's i6 optical engine takes advantage of 7 nanometer DSP technology and enables us to have over 5 billion transistors in a reasonable form factor, and that's compared to our prior generation ICE4 technology that had in excess of about 1.5 billion transistors. So we're able to do more in a smaller size, while also increasing the performance and reducing the overall power utilization. Let's translate that now into the evolution of embedded optical engines. We've generally referred to these as generations of technology, with 100 gig technology being first generation and our current 800 gig technology being fifth generation. Something you'll notice is certainly you have this idea of the top rate, or the headline rate, if you will, of the generation of technology, like fifth generation 800 gig technology enables an 800 gig wavelength of transmission. But it's important to look down below the headline rate and also realize that what we also get from a benefit is increased reach and increased spectral performance with each of these generations. And so, as an example, when you take a look at third generation 400 gig technology, while you can transmit a 400 gig wavelength a few hundred kilometers, compare that to what you can get with an 800 gig fifth generation optical engine, where we can literally transmit that 400 gig signal thousands and thousands of kilometers by comparison. That's what the evolution of technology and our innovations in terms of digital signal processing and our algorithms enable us to accomplish, which is great and helps us keep up with that capacity demand, while also giving better performance and reductions in cost, and also reductions in power. We'll take a look at some comparisons in the subsequent slides, where we take a look at third gen 400 gig, as well as second generation 200 gig. And let's do that right now. So let's take a look at if we had a current network and it was running on a third generation 400 gig optical engine technology, and we wanted to drive 800 gig worth of capacity, or service, if you will, across 800 kilometers. Well, with our third generation 400 gig technology, we would have to do what's called regeneration, and where we regenerate that signal, effectively take it out of the optical domain, back into the electrical domain, and then send it back out the optical domain as well. And because our optical reach performance is such that we can only go 300 kilometers with our third generation technology, we'll have to actually do that 2 different times, and we'll need 2 lasers to transmit the 800 gig of capacity. Now compare that to, in the green section, what you can get with 800 gig 5th generation technology. Well, we only need a single wavelength to transmit that 800 gig of capacity, and we can send that over 800 kilometers of distance. That means that with a single laser, single optical engine with a single laser, we can eliminate the regeneration, and we don't have to have that second laser that you had to have in the top picture. All of that's to say, from a benefits perspective, we can have 50% fewer sites because we can get rid of those regeneration locations. We can have a 58% reduction in power, and we can get rid of 2/3 of the lasers, or you can think of it as engines, but lasers in the network, because we don't need to do that regeneration partway through. Another example for comparison, let's take a look at a 2nd generation 200 gig network, which, if you put enough wavelengths on a fiber, you can get a total of about 19.2 terabits of capacity. But what happens whenever you have capacity demand, as we've seen in the early slides, that exceed that 19.2 terabits of capacity? The only real answer is to light up a second fiber and install a second set of equipment that will enable more capacity to be transmitted beyond the 19.2 terabits. However, if we had a 5th generation 800 gig coherent engine, we actually would be fine, because it has better spectral efficiency and it can send more capacity over a fiber pair than we can do with our 2nd gen technology. So we can save power, we can save equipment, and we can actually save costs. Let's translate that now into the central office or the data center or the location where this equipment might reside. So our 2nd generation of equipment would require 9,500 watts of power. It would also require 96 lasers, and it would occupy about 12 rack units of space. If we compare that to our 5th gen 800 gig technology, we only need 4,500 watts of power. We only need 24 lasers to transmit that, or think of that as equipment. And we can do that in 9 rack units as well. And all of that is to say, we need less power, fewer lasers, and with the increases in spectral efficiency, we've actually accomplished that while having a reserve capacity of almost another 19.2 terabits that we could deploy in that network or over that fiber optic pair for the future. So great improvement there. If we now think about the application of that equipment to compact modular solutions, which is really what we're doing and deploying today, and is growing as a high percentage of optical networking equipment. We also have the chance with miniaturization and sled-based components, we have this ability to do a pay as you grow, but also a power as you grow. And because we don't have these large monolithic chassis-based systems with centralized switch fabrics, we also don't have that power consumption that comes in when we just turn on the chassis, even though it may actually be lightly loaded in terms of line card population. So we really get this kind of incremental, buy what you need, use what you need, power what you need kind of function. I'm going to shift a little bit here now away from embedded optical engines and start talking a little bit about pluggable optical engines. There's always been a trade-off between how much size and power I can fit into a pluggable optic versus a embedded optical engine, and that remains, true today. But with Moore's law and the evolution in density of digital signal processing, with enhancements in analog optics and photonic integration, um, it's less of a stark contrast today, and we start to see pluggable optics that can achieve good performance in portions of the network. Think about the metro, while also having significant reductions in overall power. Um, we at Infinera have pioneered a technology called digital Nyquist subcarriers. That technology enables an individual laser to actually subdivide itself into independent digital signals inside of that single laser stream. We do all that in the digital signal processing domain. That was part of our ICE4 optical engine, part of our ICE6 embedded optical engine, and now is becoming part of what we call XR optics in a pluggable form factor. And the thing we're doing is exposing those subcarriers and making them individually assignable. What's the benefit of that? Well, for the very first time, we can have low speed optics, say at the edge of the network, 25 gig as an example, that can now talk to a high speed optic, say 400 gig. And if we had 16 of those 25 gig signals talking to a 400 gig transceiver on the side, we could eliminate some of the complexity in the middle of the network with electrical aggregation and the need to bookend these low speed signals. I'll show you that here as a comparison on the next slide. So let's say for a minute in the top part here, you were trying to aggregate traffic and take it back to the core part of the network. The way you would typically do that is have a set of bookended optics, 25 gig as an example, coming from the access or the aggregation part of the network. Those would terminate with additional a mated pair of optics, 25 to 25, 10 to 10, 100 to 100, at an intermediate electrical aggregation device, which usually a switch or a router, as shown here in this picture. And then on the other side of the router, you'd have a bigger port of capacity, say 400 gig, and that too would be bookended to the hub location. By comparison with XR optics, because we can have utilizing Nyquist subcarriers, digital subcarriers, because we can have low speed talking to high speed optics, we can have a simplification in the aggregation part where we eliminate the switch or the router. We can replace that with nothing more than a fiber optic splitter. And we can also then eliminate the bookended low speed optics that need to be there at the intermediate electrical aggregation point. So the net effect of that is to eliminate intermediate electrical aggregation, eliminate the bookended low speed transceivers. And another cool aspect is because these digital subcarriers are assignable amongst the optics that are present, we also can eliminate some truck rolls, because when we need to increase capacity from 25 to 50 to 75 or 100 gig, we can do that simply through a provisioning step that enables and assigns that additional subcarrier to that leaf or downstream optic. An obvious question is, so what's the ramifications of that, or how can I use that to help my network overall and make a greener network? Well, the cool thing about XR optics and digital subcarrier technology is it can be used in not just a hub and spoke manner, but it can also be used in a ring or amplified ring type of architecture. And in this case, we actually collaborated with a European service provider and worked with them to model their network. And when they did that modeling, they determined that loading their network with XR optic technology in this amplified ring architecture gave them the ability to drive down power consumption in their ring architecture by 75%, and it also reduced their footprint of space occupancy of equipment needed by over 65% as well. If you translate that savings of a single ring architecture into, well, what does it really mean from an equivalent, power consumption capability? Well, it's equivalent to taking almost 20 cars off the road, or eliminating 27,000 liters of petrol, or 151 barrels of oil, or supplying enough power for almost 23 households. If you then expand that and say, well, most service providers wouldn't have just a single ring, right? That would be good for a certain geography. What we've looked at and determined is many service providers would have in excess of 200 of these types of rings in their network. And if they did, obviously, that then translates into this XR optic change can translate into 4,000 cars being pulled off the road, or almost 4,500 homes being powered, all with a fairly modest architectural shift in the network. It's also not just about the power aspect of it. It's also about can I put less equipment and have less occupancy of that equipment in my central office that someday will be retired and will either need to be recycled or put into a landfill or some combination of the two. And one of the cool things about this technology is it also, in this ring architecture, eliminated a bunch of space, 30 rack units of space. Maybe more importantly, 10 routers were not needed to be put into the network, all of which would have to be recycled or put into a landfill at a future date. So look, we all have a role to play here. We need to continue to evolve our existing networks. We need to continue to seek technological innovations that help us create new architectures and take step functions or leapfrog forward in terms of efficiency, performance, and power utilization. But most of all, it takes people. It takes all of us. And with an ecosystem, with partnership, and a shared vision, together, we can make this happen. We're happy to be a part of your network. We're happy to play our role, and we look forward to driving future innovations into the network that can help all of us support capacity demands we need, but also help us realize a greener planet. Thank you very much for your time today. Great to be with you.